Recording in progress.
Uh, so good morning, everybody. Today we will be talking about attention and machine translation. Um, so before getting into the main problem, what is sequence to sequence model? So basically, uh, a pipeline where a sequence goes in as the input and the output is also a sequence is a sequence to sequence model. And it can be in the form of an audio form or like a sentence or so. But the problem that comes with sequence to sequence models are that there's no time synchronicity or order synchronicity. So like for example, if you see here that I ate an apple, if it's converted to German, the ate is in the last part of the sentence. So you see that the order of the words is different when it's in English and when it's in German. So that's one of the problems which we face when we're doing sequence to sequence. Um, so how can we overcome this? So basically, the model in general looks like this. You pass in words as one hot vectors, but when you're doing one hot vector, um, there's a lot of sparsity in the data, and so you would want to do dimensionality reduction. And for that, there's a projection layer, which you can see is in with P written on it, which projects down to the lower dimension and produces embeddings, which is then passed to the language model. Uh, so in the green are the hidden layers, which could be your LSTM layers or the model you define. And the output at each time step is shown in the orange boxes above. Uh, so this is how a general model looks like. Um, but before we go in depth for the model, uh, how should the input look like? So a note on beginning and the ends. So when you're passing a sentence to the model does not know if it's in the middle, if it's in the start or in the end, unless you specify it. So if you see here, four score and an eight is, it's unclear if this is the start of a sentence or end or both or just middle. So to make it very explicit, we'll give an SOS and an EOS. SOS start of the sentence and EOS is end of a sentence. So let's just do a few examples about the same. So in the first sentence, you see four score and an eight, which is like the middle of the sentence. In the second example, you have SOS in the start, which is the start, just the start of the sentence. Similarly, in the third example, you see EOS is in the end, which is just the end of the sentence. And in the final example, you have SOS and EOS with four score and an eight, which is the complete input sentence for the model. So now coming back to our problem, now that we've seen about the model in general and the data in general, let's just get into depth for the problem. So as discussed, as I mentioned before, that I ate an apple once you put it to sequence model, the order of the word ate is different. So there's a problem of order synchronicity here. So as stated, a sequence goes in, but a different sequence comes out. So how do we deal with it? So let's have an overview of the model architecture. So basically, we do delayed sequence to sequence, where you first process the entire input generated and create a hidden representation for it. So now if you see here, the one in the red box would have the entire sentence detail. So basically, you would pass the word by word to the model, but once the sentence is completely passed, only then the final hidden representation, which is created by the model, is used for the decoder. And if you can visualize this as, like, for example, in real time, if you're doing machine translation, if there's a translator, you would provide the entire sentence first so that they understand the context and then they would translate it to others. So similarly in the model as well, that's why it's delayed sequence to sequence, because you pass the entire sequence first. Uh, so, so by passing the entire sequence, the model gets an idea of the context as well of the sentence, and that the final hidden representation of the input input sequence is then used for decoder. So that is used to generate an output by the decoder. So we'll go in depth for the encoder and decoder. So the simple translation model works like this. You pass in a statement, once pass in an input. Once the input is completely given to the model the final hidden representation, which is given by the model, is then used to pass it to the decoder with the SOS token so that the decoder knows this is the start for the output. And once you pass that, at every time step, you'll get an output. And that output is then passed to the next time step and so on, so that the model has whatever has been previously as an input data as well, along with the word before that for translation. So you can see here the input is fed into the recurrent structure, and then it's terminated when you get the EOS. And similarly, you pass the SOS, that's for your output. And yeah, and then the hidden activation is passed with the SOS, and that goes on for every time step. And this happens until the last EOS is produced by the model, so that the model knows that, okay, this is the end of this output statement. So this I spoke for one hidden layer, but you can do that for multiple as well. It works the same way. Like, for example, in your homeworks also, you'll be using multiple layers, and you'll be like increasing and changing the depth of your model and stuff. So the working mechanism is in the same way. So we'll come to the encoder and decoder now. Till the, um, till the hidden value is calculated for the entire input sequence is the encoder part of this model, and after that comes the decoder. Like the highlighted sections show the same. So how is the decoder decoding the predictions? So decoder would generate a probability distribution over all the words in its data, and then take the highest probability word as the output for that time step, and then pass it to the next one. So as you can see here, there's like at each time step, the network produces the entire probability distribution over all the words, and then the word is drawn from it. So coming to the training aspect of it, so the forward pass is straightforward. You have an encoder, a decoder. The encoder would send the encoded sentence embedding values to the decoder, and then the decoder would use that. But coming to the backward pass, in backward pass, you would give the actual values as well to your model, and the model would compute the divergence between the actual value and the predicted. Like, for example, the predicted is y0, y1, y2, y3, y4 here, and the actual words are passed above. And you calculate the divergence between the two, and then you pass it to the model and do back propagation so that you upgrade the gradient so that your model performs better. So, uh, so the thing here is you could compute divergence for each word, but it'll be computationally expensive. So you could just compute it for the final word, because that has the data of all the inputs and the previous words, and then you can pass it to your network, and then do the update wherever needed. So with that, I think Hina would continue from machine translation.
Yeah. So, as Pavitra mentioned, we know that the encoder decoder is called the encoder decoder because the encoder condenses the entire input sequence to a single hidden state. And let's assume that the single vector is very high dimensional vector. And there are many ways of projecting this high dimensional vector to a two-dimensional space. We're converting it into a two-dimensional space because that is what we can visualize. And it turns out that this architecture is very successful. So here we see that there are similar, so here we can see that on the left that the similar inputs are actually getting mapped to similar locations in the two-dimensional space. So if you see in the diagram, you can see that John respects Mary, John is in love with Mary, John admires Mary. All of these three inputs are getting mapped to the lower left corner, whereas Mary respects John, Mary is in love with John, and Mary admires John. All of these form a different cluster because they're not the same thing as what we saw before. So we see that the similar inputs are getting clustered to each other, whereas we see that there are two different clusters that are being formed, but they still share a spatial relationship. So when we look at these diagrams, we can notice that there is some kind of structure that is getting created during the encoder-decoder training. And this is an interesting thing that we got to know through this. So also in the word-to-vec that we have seen before, it's an interesting instance of word embeddings, and the same thing happens there as well. So each word gets turned into a vector by the word-to-vec algorithm, and then this vector is also in the very high-dimensional space, but then it can be projected to a two-dimensional space. And what we notice is that if we take the vector for, say, king, and you subtract the vector men from it, and then you add the vector women to it, you end up with the vector queen, which speaks to how semantic these encoding methods can get, and that's pretty interesting. So coming to the next slide. So of course there are problems with this framework, and the immediate problem that you can notice is that one node is particularly being overloaded with a lot of information. So if you have a vector with two dimensions, two dimension is not like a high dimensional vector, but then you have two dimensions, and there's only limited information that you can encode in that two-dimensional vector, and there's not a lot of information as well. And you can make this vector arbitrarily high dimensional, but then that is going to make it very difficult for you to train. And if you have longer and longer sequences, there'll be infinitely many possible input sequence that you could encode, but there are no finite ways that you could encode all the information into the possible input sequences. So one node is particularly getting overloaded with a lot of information, and this becomes the problem with the encoder-decoder framework. So the idea to resolve is that the hidden state gets produced every time step, right? The orange boxes that you see there, for every time step we have a hidden state, and if we, after the entire pass of the encoder, it's overloaded, then we might just use a collection of different hidden states for decoding. So if we are decoding for the first time step, uh, and you can see the output of that is ich, which you know in ich in German means I in English. So maybe in that time step, we should use the hidden state at the first time step of the encoder more, because the first time step of the encoder, we are just dealing with I here. And the hidden state has more relevant semantic information. So the basic idea of this slide is that since one node is overloaded, we might just use a collection of input hidden states to do the decoding rather than just relying on the last time step. So we saw that in the previous encoder-decoder model, all the combined information from all the previous states were overloaded onto the last hidden state. And to overcome this, there was a modification to that model where we use the average of all the hidden states of the encoder, and then you feed it to the decoder. But again, if you see this architecture, there is one obvious problem that is associated with this architecture as well. The major problem is that all the words are being given equal weight. And we're trying to say that apple and ich are the same weight as I and apple, which is not what you want. So as a modification to that, we then came up with weighted combination. In weighted combination, what we're trying to do is that we're trying to take the outputs of all the hidden layers of the encoder, and then we're trying to compute weights through backpropagation, and then using all of these weighted combination of my encoder hidden states to feed it to the decoder. So in this way, whenever there's a decoding of apple, there is high importance or high weightage that is being given to the word apple rather than I ate or the end of sentence. So the main idea behind this is like this is what we know as attention. And here we take the weighted combination of all the encoder outputs and feed it to the decoder, along with the previous prediction of the decoder. So in this way, we're giving more weightage to the word that needs to be more prominent. Okay. Coming to the next slide. So here, in the attention models, the weights are dynamically computed through backpropagation of the loss, that is calculated between the divergence of the ground truth and the predicted output. And the gradients are backpropagated, and the weights are calculated for the encoder. Yeah. So here, when we are calculating this weight, we are calculating the weights with respect to the energy function. So energy function takes in the hidden state as well as the decoder's previous output, and it's being fed into the function G. What this function G is, I'll be explaining in the upcoming slide. And for the energy function, we're basically computing a softmax. Here, as an intuition, you should not think of softmax as a probability distribution. Rather, it's more of a relative weightage of a given word with respect to all the other words in the given sequence. So in the previous slide, I'd mentioned about the G function. So this particular G function is used for computation of the energy, and it is just a dot product between the hidden state and the decoder's previous state. As you can see in the equation first, in the first equation right there. And this G function could also have a transformation between the previous state and the decoder's previous hidden state. So WG in the second equation that you see is a learned parameter. The first one is more useful when both the dimensions of the encoder and encoder hidden state and your decoder's previous state have the same dimensions. But suppose in the second equation, we use it more when your encoder's hidden state and your decoder's previous hidden state have a dimension mismatch. So then we use a transformation WG. Uh, and then there are also other ways. What we could do is we could use functions like an MLP, which can be used to find the correspondence between the decoder's previous hidden state and the encoder's output. Again, as I mentioned, usually by default, most of us use the cross attention, which is the first equation that you see right there, where we just multiply the encoder's hidden state with the decoder's previous prediction. And then we compute the weights. So these weights are then multiplied to the encoder's output and then fed into the decoder network.
So which one is most used in practice?
The first one, the cross attention equation.
And it does it provide the most efficiency, and if so, why don't we use the other ones?
Yeah, so the first one you'll use when when the dimensions are matching. Your encoder's hidden state is matching with the decoder's previous hidden state. The dimensions match. But in case there's a dimension mismatch, you would use a second equation where you have to bring in a WG, a transformation in between, to like overcome the dimension mismatch that you had encountered in the first equation.
So when would we use like an MLP or a tanh function?
Yeah, those are also different ways of just handling the dimension mismatch. There are different ways. You can use different ways to like get over the dimension mismatch that you encountered, that you will encounter.
And there's no real difference in performance. It's just about the weight mismatch.
Yeah, yeah. Okay. Yeah. So coming to the next slide. So for decoding, we know that in the decoder, we need something called as a S of -1, which is used as the initial hidden state. So what are the various options that we can have for this particular hidden state? One simple option, what we can think of is to set it as all zeros, which is not a good thing. And then second thing, what we can think of is that we can make the hidden state as a learnable parameter, or we could alternatively just use the last output of the encoder and use it as the initialization for the decoder again. But if there is a mismatch or something, then again, like as I mentioned in the previous slide, we can use a transformation between them. So S of -1 now will be my weight times the last encoder's hidden output. So once we have the initial state S of -1, we get the weighted combination of H and S, and then we compute the context. This context is going to be fed along with the previous prediction from the decoder, which can be used for predicting the current word at this current time step. And this process continues until we reach the end of sequence symbol. So one modification to the architecture, to the previous architecture, was introducing the query key value. So basically in this architecture, we split the hidden states into a key and a value vector. And similarly for the S of -1, which I discussed previously, which is nothing but your decoder's hidden state, that is turned into a query vector. So basically a query is a characteristic of the decoder, and the key and values are the characteristics of the encoder. The decoder will send now a query to the encoder, and using the key, the encoder will return a value. So these keys and values are computed by taking the hidden vector and it's multiplied by some weights. These weights are actually learned parameters, so all the words initially are like same. Like all the red vectors that you're seeing there will have same weights, and the green vector also have the same weights. So the energy function, as I said in this case, would be the query and the key and find the dot product between them, and then we apply a softmax where we get the weights, and then using that weights we multiply to the value. So previously we multiplied the weights to the hidden vector itself, but here in this architecture we are multiplying the weights to the values that are produced from these encoder hidden states. The main advantage that of this is that the queries and keys determine which portion of the input should I give more attention to. For example, when I'm predicting apple or something, I want to give more maximum weight to apple rather than the other words present in my vocabulary. So basically, what does the attention module learn from all this? So as I mentioned, we have the weights, the query, and the key that are generated by multiplying the hidden state by some transformation to form the key and value. So we have the learnable parameters for the query weights matrix, and then the key weights matrix, and then the value matrix as well. There was another modification to the same architecture, which is the multi-head attention. So previously, only one single head attention we were using, where you just had one query, key, and value for all the hidden states. But now we have a subset of queries and keys and values for each of these hidden states of the encoder and decoder architecture. So one attention head would, so you can think of it as like one attention head would focus on the relative positions between the words. Another attention module could pay attention to the punctuations in the input sequence or something. And in the end, what you're going to do is you're going to take all the attention vectors that are present and concatenate it and then pass it to the decoder for decoding it. This is the extension of multi-head attention. So one trick that Prof would have mentioned in the lectures is the teacher forcing method. So what teacher forcing does is that it's a process where you're cheating the architecture, where you're trying to initially, train the architecture. So initially when you're training it, you know that the decoder will take inputs from the encoder as well as the previous decoding of the decoder. So initially your network hasn't learned much. It will have some erroneous predictions. So once you predict an erroneous prediction in the time step T0, that will be continued and it will get carried on to all the other time steps. So to avoid that, we are initially training the network. When we are initially training the network, we will use a teacher forcing of 100%, where we are feeding the actual ground truth as the previous input in the decoder, like below that we see, along with the encoder output, so that we get correct prediction and the network learns much better this way. And as the training progresses, and once we get a good validation accuracy, we keep reducing the teacher forcing rate and keep passing the previous prediction for the next time step. And for back propagation, we basically computed the divergence between the target output and the output distributions, and then we back propagate all the derivatives through the network. Any questions? Yeah. So in this slide, you can see that this is known as an attention map, and it mostly looks like this diagonal that you see there. And it gives the correspondence of the weights where any given word is being concentrated while predicting these outputs. For example, when we are predicting the word agreement, you can see that agreement correlates with the word accord. So basically, accord is being most weighted when we are predicting agreement. And here you can see that the gray color depicts less attention, whereas the white color represents maximum attention that is being given to the corresponding word and translation. So this you will encounter in your homework for part 2, where you will have this attention map. This will be covered in the bootcamp as well, homework for part 2 bootcamp. But just to make sure, and please do make sure that your attention map looks like a diagonal when you're training it. So now we'll go through a few examples where we use it. So this is an example where in a sentiment analysis, when the network is trying to predict some sentiments, it's highlighting the portion of the sentence that the network paid more attention to while predicting the particular sentiment. You can see all of that in yellow highlighted here. Okay, so attention models can also be used in image captioning. So here you can see that given an image, you're trying to predict what the image actually does. So when you actually back propagate and check where the model is actually paying more attention, you can see that, suppose in the first example, you can see that a woman is throwing frisbee. So frisbee is getting more attention than other parts in the image. And similarly, in the second image, similarly in the dog image that you see, you'll see that the dog's face, if it's present or not, that's being given most attention to than the other parts. And that's how it's working for the other images as well. So yeah, I mean, that's all from our side. I would also recommend all of you guys to go over the listen, attend, spell paper, which from Google. That would be really helpful for homework for part 2 before you guys actually start working on it. And a lot more things would be discussed in the boot camp as well.